Okay, Bismillahirrahmanirrahim. Now, the semiconductor diode and its application. So, PN junction diode, we have studied the P type and N type in the previous lecture. So, now by combining these two type of extrinsic materials, a device is introduced that is called the diode. Okay, so it's a symbol, and you can see that that it's a unidirectional device. Okay, because it allows the current in the forward bias and it blocks the flow in the reverse bias. Okay, so this side is P and this side is N. Okay, and this plus minus shows a barrier voltage. Okay, so it is a semiconductor device with a PN junction. It is a one-way device, allow the current to flow when it is forward bias. Almost totally blocks the current flow when it is reverse bias. Therefore, a diode is a two-terminal component. Okay, this is the anode side, this is a cathode side, and this is the forward condition. It has two electrodes called the anode and the cathode. Anode is attached to the P side and cathode is attached to the N side. The diode power classifications are referred in this figure: low current diode, medium current diode, and high current diodes. So the low power diode, usually small diodes can handle low current up to 100 milliampere. Power dissipation will be less than 800 milliwatt. While in the high power diodes, large diode can handle high current of 1 up to 10 amperes. Therefore, these are used in the power electronic side. And the power dissipation will be between 1 watt and the 10 watt. You can see the table for the small, the medium, and the large diodes. Okay, the cathode identification. Okay, color band it can be assembled as, and it can be known by the color band. Okay, so it can be identified by the color band, the diode symbol, and it can be identified by the diode symbol, and it can and the large are identified by the threaded portion. Okay, so in forward, there's a list of the current in the forward bias, and this is the list of the current in the reverse bias. Okay, so now, as you know, we have for any diode we have the voltage current characteristics. Voltage is on the mm, x-axis while the current is on the y-axis. So as you can see that this is a silicon diode, so a minimum of 4.7 volt is required in order to cross the barrier. So as the 0.7 is reached, now it shoots. Okay, so and the flow of current is caused. So this is delta IF. Delta means a change of current, and F is in the forward bias. Now the current, the reverse bias, you can see that by this way the voltage is applied, and we are increasing the voltage on the reverse side, but the flow of current is not increasing uh, accordingly. So mm rather a threshold is causing, and an avalanche is caused. By this way, the diode is damaged by flowing a huge amount of current which cannot be bearable by any diode. So we can say that in the reverse bias, the diode cannot flow. Okay, so this was the current characteristics. Okay, now this is the diode equation: I is equal to I naught e raised to the power Vd over eta Vt minus 1, and that is approximately equal to I naught e raised to the power Vd over eta Vt. Okay, I is the current through the diode in amperes, and Vd is the diode voltage with the anode positive with respect to the cathode in B, and I naught is the leakage or the reverse current. And eta is the empirical constant known as the emission coefficient or the ideality factor. Vt is the voltage equivalent of the temperature, that is equal to kT over Q. K is the Boltzmann's constant. T is the temperature and Q is the charge. Okay, so as we can see from this characteristic curve, up to zero point 0.7 volt, as the forward bias is increased from zero point 0.1 to zero point 0.7 volt, the diode hardly conducts. The forward current is very low, that is less than 5 milliampere. And when the 5 zero point 0.7 volt reaches, so beyond the zero point 0.7 volt, the forward current increase very sharply. And increasing the forward bias beyond, say, for example, 1 volt will destroy a diode due to extensive forward current. So a current limiting resistor is needed in the circuit to protect the diode, because as you know that the resistor can limit the current flow. And in the reverse characteristics of the silicon, when the voltage is applied from 0 to 75 volts, this minus indicates the flow of current in the reverse bias, means p type is connected to the negative terminal of the battery and n type is connected to the positive terminal of the battery. So as you can note, the change of the scale in the y-axis between the forward and the reverse characteristics. Reverse current IR is often very low, not more than 1 microampere for the reverse voltage up to 75 volt. Even 75 volt is applied, but the current is not more than 1 microampere. On the other hand, when just 1 volt is applied on in the forward bias, so uh, the huge amount of current is flow, which cannot be even bearable by the diode. Okay, IR is negligible compared to IF. For all the practical purpose, diode behaves like an open circuit in the reverse bias. Okay, and in the forward bias, it acts as a short circuit. Okay, now a current limiting resistor is introduced. Okay, that is the IV characteristic curve of the germanium, and as you know that the depletion voltage for the germanium is 0.3. So the same story of the forward bias and the reverse bias uh, in this germanium as it was in the silicon based diode. Okay, so we will move forward. Okay, the variation of the forward voltage or the threshold voltage with the temperature. So as we can see that it is there is an effect of the temperature on the characteristic or the threshold voltage of the diode. So we know that the silicon diode has a forward voltage of 0.7 volt, but that is at 25 degrees C. Okay, remember. And the germanium is zero point 0.3 at means the room temperature. Now the temperature coefficient of the silicon is given by KTC is equal to minus 2 millivolt per degree centigrade. Okay, for each degree centigrade, the K is equal to minus 2 millivolt. Temperature coefficient is negative, means that the forward voltage decreases as temperature increases. Okay, these two are inversely related. So by increasing the voltage, by increasing the forward voltage, it will decreases the temperature. Okay, find the now we have to there is a question, find the threshold voltage at 100 degrees C for the germanium and silicon. Both of the silicon and germanium made diode, you have to find the threshold voltage. Now in this case, there is a the room temperature is not given, but a temperature of 100 degrees C is given. So the answer is 0.15. You can find it by this relation. Okay, minus 2 millivolt per degree C. Okay, now a reverse bias breakdown mechanism. So there are two cases. The one is a very narrow depletion region, and the other is depletion region very wide. So now first start with the case 1. Okay, now the reverse voltage provides very high field strength. What is the field strength? The question arises. So the voltage per distance is called the field strength. Okay, means kilovolt per centimeter. We can also say it a dielectric intensity. Okay, electric field intensity, and in dielectrics we can say that we usually use this terminology electric field intensity, and that is in the volt per distance. Okay, volt per meter. As in the dielectric, for example, the field strength of the air is 21 kV per centimeter. So that is actually the voltage that it can withstand. The electron break away from their atoms due to this field strength. Due to this electron flow, depletion region is converted into the conductor from the insulator, and this is called ionization by electric field. And this is known as the Zener breakdown mechanism. Usually occur when the reverse bias is less than 5 volt. Now, the second case, in the reverse bias mode, the reverse saturation current flows. There are electrons moving in the reverse saturation current. When these electrons travel in the wider depletion region, these electrons gain a lot of energy. And these energetic electrons collide with the atoms, with other neutral atoms, and cause their electrons to break free. So due to these new electrons, more collision occur and more electrons gets release, and this by 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 more and more collisions, and a flood of electrons is ionized, a flood of electron is caused. So this flood of breakdown of any insulator is called what? The avalanche. Okay, by this way, the insulator is converted to the conductor. The dielectric is converted to the conductor, because in dielectric or the insulator there are no free electrons, no ionized electrons. So as soon as the collision is causing, so the neutral atoms become ionized. It is converted to the ionized form. So by having a large number of ionized particles, so this substance will no more be an insulator. Rather, it will be converted to the conductor. So this process is called the ionization by the collision. Okay. Uh, for your information, the ionization can be caused by many other agencies. By You can cause the ionization by the light, by the sound energy, by the pressure energy, by the voltage. But in this case, the ionization is caused by the collision. Okay, so it usually occur when the reverse voltage is greater than 5 volt. Okay, now what is the reverse saturation current, ICO? These occur during the reverse bias condition. When the diode is reverse bias, we know the depletion region width increases. Therefore, no current flows happens due to the majority carriers. However, minority carriers diffusion through this depletion region. In a PN junction diode, the reverse saturation current occurs due to the diffusion flow of electrons, minority carriers from the P region to the N region, and flow of holes, that is the minority carriers from the N region to the P region. So this current is nearly constant and is known as the reverse saturation current, and you can see this current in the reverse bias condition of the IV characteristic curve. So is there any relation of ICO with the temperature? Yes. Reverse saturation current is now science. Uni new science. It increases rapidly with the temperature. The increase is of the order of 7% per degree Celsius. for both germanium and silicon. In other words, ICO doubles for every 10 degrees C rise in temperature and is definitely serious. So you can find the I2 after rising the temperature by this relation. I2 is equal to I1. I1 is the current when the temperature is T1, and I2 is the temperature. I2 is the current at the temperature T2. Okay, so after rising the temperature, the current will be I2. Okay, now we have a problem on the basis of this formula. Calculate forward resistance of the germanium diode at IF is equal to 60 milliampere. So at IF 60 ampere, VF is equal to 0.33 volt approximately. Therefore, forward resistance R is equal to V over I. So as we have already discussed that a current limiting device, that is resistance, is needed in order to limit the current in the forward bias current. As if you remember from the characteristic curve, just the flow, just providing a 1 volt in the forward bias causing a huge amount of about 100 milliampere of current, and it will damage the diode. So therefore there is a need of the current limiting uh, resistor, and by this formula you can find the R in the forward bias current of forward bias condition. Okay, RF is equal to VF over IF, 0.33 volt over 60 milliampere, and uh, the optimum resistance resistor need is 5.5 ohm. Okay, so here is a current limiting resistor for this forward bias condition. Now example 5, 2.5, very simple. VR is 20 volt at VR is equal to 20, IR is equal to 90 nanoampere. Okay, so these values are actually obtained from the curve, IV characteristic curve. Now you can find R in the reverse bias as well. So 2 to 2 mega ohm, because a flood of electrons is caused in the reverse bias. So very high and large value of the resistor is needed in the reverse bias. Okay, so now some of the important diode parameter: VF, the forward bias voltage; IF, forward current; VR, reverse; RD. Now this is the new term, the dynamic resistor, and this is equal to the change in the VF over change in the IF. This is actually shows uh, the slope of the IV characteristic curve. Okay, so VBR, the breakdown voltage, that is 50 volt for the germanium and 75 volt for the silicon. So the dynamic resistor RD is equal to change in the VF over the change in IF. So a numerical based on this relation is: what is the dynamic resistance of a diode with the forward current of 5 milliampere? So RD is equal to 26 millivolt over 5 milliampere is equal to 5.5 volt. Okay, now for the dynamic characteristics shown in figure 2.8, determine the dynamic resistance at 40 milliampere. So you can get the voltage from here. So IF is equal to 40. So for the 40, the voltage is 0.72. So the change in the voltage is 0.726 minus 0.71. Okay, this to this. So and the change in current is 60 minus 20. Okay, so IF will be 40 by 60 minus 20, so you will get 40. So that is why uh, 60 minus 20, so the corresponding current for the 60 is 0.726, and the corresponding voltage for this 20 IF is 0.71. So that is why we have subtracted this from this. So you will get 0.016 volt. Now 0.016 volt divided by 116 milli ampere. Okay, so we will get zero point 0.4. This is not the volt, this is actually the ampere. Okay, so zero point 0.5, zero point 0.4 ohm. Okay, what is the ideal diode? The ideal diode is in the forward bias condition, it will have no forward resistance and will not drop any voltage across it. So RF will be equal to 0 and VF, as the resistance is 0, so the voltage drop across this diode will be equal to 0. So this is the actually the condition for the ideal diode. Okay, and in the reverse bias condition, the resistance will be very much high, means infinity. So that is why we will have a voltage drop of infinity, and because of this huge amount of the resistance, no current will be flow. So this is actually the forward bias is actually the case of the short circuit, and the reverse bias is actually the case of the open circuit. Okay, now these are the diode characteristics, ideal diode characteristics. Okay, and this is the germanium diode characteristics for the ideal diode, and silicon. Okay, now the practical diode will have these values. These are the ideal diode characteristics, and this is the practical diode. Okay, as we have studied earlier. Now construct a piecewise linear characteristics of a germanium diode, given that its dynamic resistance is zero point 0.6 ohm and forward current is 100 milliampere. So you look at this figure. This is the given figure, and this the initial value is zero point 0.3 VF, and the current is 0, and in this case the voltage is 0.36 volt and the current is 100 milliampere. So the first value shows the voltage, the second value shows the current. So mark point A, this is point A and this is point B. So how we have find the B? So 100 minus 0 is equal to 100. Okay, and 100 into, now VF is equal to 100 into RD. 100 into RD, this is given zero point 0.6. So 100 into 0.6 is equal to 60 millivolt, which is equal to 0.06 volt. Okay, so the point B is equal to zero point 0.3 plus 0.06. This is zero point 0.3, and the point B is 0.06. So adding this we will get 0.36. Okay, and the ampere is 100. So these are not the given values, rather we have find these values by this way. Okay, and this method is called piecewise linear characteristic method. Now the DC equivalent characteristics of the diode. This is the ideal diode, no voltage drop. This is the simple DC equivalent circuit for the practical diode, and this is the DC equivalent circuit for the complete. Now we will have the RD, the dynamic resistance. This is the voltage, forward bias voltage required, that is zero point 0.3 for the germanium and zero point 0.7 for the silicon. And this is the diode symbol, which shows the unidirectional characteristics of this device. So now example, the problem 2.7, which is very simple. So that is your homework. Okay, now you can see a DC load line. Okay, so this is a DC load line, which you can find by this slope formula, negative slope formula. Okay, that is equal to minus 1 over RL. We have already discussed in the class lecture. So now in order to find the QC point, so you have to draw a diode characteristic curve and the DC load line. So the point where these two coincide or intersect. So this point is called the QC point, or we can say that quiescent point, or we can say it is a Q point, quiescent point, or simply Q point. So you have to find the quiescent point for this diode, and we have already discussed this in our last lecture. So that is your uh, homework. Okay, so that was all about this the part 2 of the first week lecture. I hope you will understand this. Okay, so that was all about and that is the end of the first lecture, first week. Thank you.